I'm Tania Morimoto, and I'm a 2022 Beckman Young Investigator. I'm currently an associate professor in the Department of Mechanical and Aerospace Engineering at the University of California, San Diego, and my research is broadly focused on the design and control of flexible and soft robots for unstructured, unknown environments, such as inside the human body. Flexible surgical instruments, including, for example, endoscopes, colonoscopes, and catheters, have several limitations that can lead to potential procedural complications and harm to the patient. For instance, their low number of degrees of freedom and manual control can make it difficult to reach certain regions of the anatomy. In addition, when pushing the base of these instruments in order to navigate through highly curved cavities, there's a risk of perforating through the cavity walls, resulting in severe complications. Thanks to the Arnold and Mabel Beckman Foundation, my group has been exploring a new type of soft robot that can snake its way through the body while imparting minimal forces to sensitive surrounding tissues. These robots, known as soft-growing robots or vine robots, navigate by extending or everting material from their tip. Importantly, the body of the robot remains stationary even as the tip moves forward, meaning minimal forces are applied to the surroundings. While other groups have explored these robots at a large scale, my group is focused on answering questions about how these robots can be scaled down to sizes relevant for medical applications, how we can accurately steer and retract these robots, and how a human operator should actually interact and control them. To start, we can see that a simple growing robot without active steering can have trouble safely navigating environments like the colon. We therefore propose the design of an inchworm-inspired robot that sits inside the body of the growing robot. This inchworm robot is pneumatically actuated and can bend in any direction, enabling steering. It can also pull the inverted material back inside the body of the robot to enable safe, controlled retraction of the entire system. In order to scale these robots down to the millimeter scale, however, we had to come up with alternative methods of actuation. We realized that embedding a thermally actuated material into the skin of the robot could enable high curvature bending while ensuring that the robot remained completely soft, allowing it to still squeeze through tight spaces. Using liquid crystal elastomers, or LCEs, we were able to create millimeter scale growing robots that could bend at multiple locations along their body to navigate highly complex paths. By controlling either temperature, pressure, or a combination, we could achieve a wide range of bending angles. This approach has significant potential to improve navigation through complex environments, including, for example, the vasculature. Current practice relies on pushing and twisting semi-rigid catheters from the base to navigate the blood vessels to remove a blood clot in the brain. Our approach can potentially make this navigation and turning much easier to perform, even when the required turns are particularly sharp. We've also investigated a number of other growing robot designs, all with enhanced functionality. For example, we investigated an approach to enable variable stiffness of the robot that allows for virtual joints. We also explored multi-material designs that enable improved contact-aided navigation of challenging, bumpy environments. We also developed an alternative method for controlled retraction of small-scale growing robots that relies only on the kinking of a small additional channel. This design opens the door for growing robots to be used in numerous applications. Finally, we explored alternative methods for steering, including embedding magnetic material into the skin of the robot and using robotically controlled external permanent magnets to control the direction and the amount of bending of the robot. This research and more was only made possible due to the Beckman Young Investigator Award. Dr. Arnold O. Beckman was one of the greatest inventors, and his scientific instruments were truly transformational. He has served as a huge inspiration for the work in my lab as we also seek to invent new instrumentation that really pushes the bounds of current technology. Dr. Beckman took a highly multidisciplinary approach to revolutionizing the way we study the world. By working at the intersection of many different fields, he was able to discover and invent influential devices and instrumentation. This approach is one that I have been aiming to follow in my own research by tightening connections with other disciplines, including, in particular, connections with materials researchers, since I believe that the integration of new soft materials will be critical for enabling truly transformative medical devices and instrumentation. I have also found that Dr. Beckman's idea that necessity is a stimulus for invention has provided me with helpful perspective both in research and outside the lab. He said, "If my classmate hadn't come up with his lemon juice problem, chances are I never in the world would have thought about making a pH meter." This sentiment has helped me to look at problems with a new perspective and has helped me to focus on viewing all problems as an exciting opportunity for discovery and invention.